Hi, the purpose of this video is to talk to you about Chapter 6, the normal distribution. This video intended to cover just part of Chapter 6, as we won't cover the whole thing, but we'll start about Chapter 6, 6.2, and we'll move through from there. There are some concepts here that I think warrant going back over. By this time, you should have listened to the video on the normal distribution that's a little bit more animated. But about now, it's a good time to sort of dip back to that and make sure everybody is really on board with this. This is a critical concept in understanding statistics. The standard normal Z distribution is what we are referring to when we speak about the standard normal distribution, or the Z chart, or as I often refer to it as the LeBron James of statistics. It's important that you understand that the standard normal Z distribution is really just a special case of the normal distribution. It is a case with which we are able to transform many things that we do into a way more useful method. We do this by making several assumptions that go along with this standard normal Z distribution. The first assumption that we make is that the mean, or the midpoint of the normal distribution that you see in front of you, is always going to take on the value of 0. That is the midpoint. The entire distribution as we see it here, whole thing, all adds up to 100%. Every time we see the special case of the normal distribution, we know that the mean, the midpoint right here, is 0, which we often refer to as mu, is going to equal 0, and the entirety of the whole distribution will always add up to 100%. Knowing that this entire distribution adds up to 100% and that the mean is always 0 helps us to be able to transform data that often has different scales, and we'll get to that later, into something where we are able to compare this group to that group. Take, for example, if we had done a survey, and on one set of questions we asked, rate your happiness with this procedure on a scale of 1 to 5. And then on another similar survey, we might have said, rate your happiness with this particular thing on a scale of 1 to 7. In that case, we would need to somehow make these two scales equal, because the mean of one scale would be obviously different than the mean of the other. And if they were testing the same thing, we would need some way to make these things equal. The standard normal Z distribution is just what we need to make these sorts of things equal. So we do this by making the mean equal to 0, and then we consider the standard deviation. Every standard deviation will be equal to the value of 1. So as you can see, I've tried to write on here as best I am able. I'm learning to use this writing on the screen here. You can see that I have indicated that a standard deviation, which you ought to be relatively familiar with at this point right here, is equal to 1, and over here, of course, is also equal to 1. Generally, when we look at this, we consider about 3 standard deviations. So that said, we would have probably another one about right here, and possibly another one about there, and then one over here, and one over here. So from this slide, it's important to understand that when we use the standard normal Z distribution, it's a special case of the normal distribution where the mean, right down here, is always equal to 0, right here. And the whole curve, the whole thing, this whole bit, adds up to 100%. of course, making each side, the yellow side, equal to 50% and the green side also equal to 50%. And each standard deviation has the value of 1. Now, related to this is something called the standard normal z-table. If you have ever had a statistics class, which I assume most of you have absolutely been exposed to the standard normal z-table. As a matter of fact, if you want to pause this video and take a look at your appendix 1 for this textbook, you can see a standard normal z-table. And this z-table gives the cumulative probabilities for z based on the normal distribution that we saw on the previous page. So, as I explained in my normal distribution video that's just dedicated to this topic, it is always a standard measurement. One standard deviation between the mean, mu, being 0, and plus 1 standard deviation that is always going to be about 34% of the distribution. Likewise, between 1 standard deviation or negative 1 standard deviation and the mu of 0, we'll have another 34% of the population. So let me show you what I am talking about by using just a picture of the normal distribution. So let me show you how this looks on a z-table, and then we'll take a look at it on the normal distribution. So here we can see that on a table of positive z values, 0, or the midpoint that I showed you on the very second slide, is going to be 50%, right? Because if the whole distribution adds up to 100%, then half of it has got to be 50%. If we go to the other end of the distribution, so here we've got negative values, so here we're at negative 3.9 standard deviations, we are talking about being way out on the tails of that normal distribution. So there's pretty close to a 0% chance that something like this is going to occur. So let's just stop for a minute and talk about something that has not a lot to do with statistics, but something like LeBron James. One of the reasons I use LeBron James in my other video about the normal distribution is because he is very much on what we call the tails of the distribution. There are very few human beings alive on the earth that are 6'10" and can jump as high as he can jump and have his eye-hand coordination. He is what we call on the tails of the distribution, which means the probability of him occurring, just his size, his intellect, and his capability is very tiny. Now, we never say that it is impossible to have someone like that, but we say the possibility is very unlikely. So that's when we get out in the tails of our distribution. So let me show you what I'm talking about with a picture, because I like to think in pictures. So hopefully you'll get to that. Here we have just your basic normal distribution. And when we're talking about someone like LeBron James, we can guess that he is way out here in the tail, what we say the tails of the distribution. While it is possible for people to have the athletic ability and other stuff that he has, it isn't likely. So this is where we're going to put LeBron James right here. We'll put him out here on the ends of the curve. Whereas the rest of the NBA basketball players, they're sort of in here. They're very good at what they do, but their scoring, their rebounding, their jumping capability, it's a little bit more normally distributed. It's excellent if you were to take them and put them on a normal distribution with your basic high school player. Of course, these NBA players would all then slide way out on the end of the distribution. But if you're comparing LeBron James to just the average player, then this is the way it would look. Now, there are other players like LeBron James, don't get me wrong. I'm just using him because most people know who I'm talking about. So let's go back to a little bit more detail about the normal distribution here. So we use the normal distribution to find the probability of a particular event occurring. So let's just say that, for example, we had some problem where we did a transformation, which I'm going to show you in a second, and we came up with a z value equal to 1.52. Okay, that would mean that our event, whatever it is 1.52 standard deviations from the mean. So if we go down here and we look at our normal distribution, remember we've got our midpoint here, which should be a straight line, and our midpoint is always going to be equal to 0, right? Because that's the mean, mu, of our population. We've got plus 1 standard deviation right here, plus 0.52 more of another standard deviation. So the second standard deviation would be right here. And we would annotate this. I'm going to draw this on down to here so you can see. So this would be plus 1 standard deviation. And then this one here would be plus 2 standard deviations. And here our value is kind of in between. Now we know from other stuff that this distance right here, or this amount of the normal distribution, is always going to be 34%. So we need to add this 50% because from the origin all the way to here is going to be 50%. So we know that the probability of our event is at least going to be, let's see, where's my pen here? The probability is going to be at least 84% because we've got 50 plus 34, so that's 84%. But what we do now is go take a look at our z-chart, and that's going to tell us exactly where this percentage right here, the distance between this dot and this dot, actually measures in terms of the normal distribution. So if we go look up 1.5 on the left side of the chart and follow over to 0.2, we find this number 0.9357. So we knew it was going to be greater than 84%, and it's actually roughly 93.57%. So the way we interpret that is, if we return a z value of 1.52, then we have a 93.57% chance of this event occurring. Now we can do the same thing for negative probabilities. So remember, it's a cumulative probability. So if we were to return a value of, say, 1.96, but it's negative, we know now we're on the left-hand side of our normal distribution here. Where did my pen go? Over here. So we're way over here because we know it's negative. Remember our 1.52, here's our midpoint. Our 1.52 was about right there from the previous slide. Roughly, I don't know exactly, but that's good enough. And then now we're talking about negative almost 2 standard deviation. So this is negative 1 standard deviation. Negative 2 standard deviations is going to be about right there. So we're at 1.96. So we know that this is the same 34% that it was on the previous slide. We also know that the distance between here and here is about 13.5% of the distribution. You can't really read that. It looks like 135. So we know that right off the bat, we've got 100% is the whole chart, minus 34%, excuse me, minus 50% first, because we've got this whole thing, which we're not going to include because we're over here on the left side. Then we've got to subtract off our 34%. Then we've got to subtract off our 13.5%. And we know that equals about 2.5. So I'm using whole numbers. I'm taking 100 as opposed to 100%. I'm subtracting 50, then 34, then 13.5, and that gives us about 2.5. So that translates to about 0.0250 or 2.5% chance of this event occurring. So you notice that this number here, 0.025, is, of course, almost exactly the same as the number here because we just arrived upon it a different way. But doing it the way I did it is a really helpful way to learn how to interpret these z-values because they can be tricky when they go from negative to positive. It's worthwhile to try to do it this way, at least initially, to sort of get a handle on how to do it. Now, another slide that I think is important is this. This is something that you'll want to write down and have with you when you take a test or anything. Of course, all the tests in this class are always going to be open notes, but this is really a critical drawing, if you will. So let me explain it to you. Basically, we know that the whole normal distribution, as I stated, is 100%. And what this does is sort of break it down for us. It says that between the 1 standard deviation lines, we know we've got a 68% chance of it occurring. It's the most common. So 34% here and 34% here. I'm struggling with my pen, guys. I'm sorry. So we know we've got 34% on either side of this. By the same token, we know that between this standard deviation, between -2 and +2 standard deviations, we have a total of 95.44%, and that's because each of these contain 13.5%. And then the final tails of the distribution, these last, the third negative standard deviation or plus standard deviation, contain about 2.5% of the distribution, or a little less. So the total then comes up to this 99.73%. So again, that is from right here, +3 standard deviations and -3 standard deviations. And that is because each of these have about 2.5% of the population. And of course, each side equals 50%, or the whole thing is about 100%. So again, this is something you kind of want to get down because it's super useful. So now what we're going to do is move on and try a problem using the Z formula calculation. So this formula that you see in front of you, Z equals X minus mu over the standard deviation, allows us to calculate that Z value that we were talking about before. Remember I said we'll get to that in a second. So in a previous example, we came up with 1.52 was our Z value, that number right here. So in this is the formula that we're using. Now let's take a look at this formula for a second. What we're doing is we're taking our value that we're interested in right here. That's our value right here. We're subtracting the mean from it, and we're dividing it by the standard deviation. So we are essentially looking to see how far our value is from the mean by using standard deviations. So we do this with standardized tests. When you take the GMAT, for example, what they do is they take your score, and that would go here, your value, and they subtract from it the test mean for the sitting that you did or in that year or whatever. And they divide it by what's called the standard deviation, and that's the amount of variation that we see around the mean. And they tell us then, they give us a z-value, and that tells us how many standard deviations away you are from the mean, whether you're higher or lower. And then with this, we just convert this number using our z-chart. And then that tells us you're in the 99th percentile if you scored, 780 or whatever the top value is. So let's try an example so maybe it will make it a little easier to understand. Okay, so like I said, we're going to do this example here. So let's just imagine for a minute that we took some test in this management aptitude, and we know that the management aptitude test is normally distributed with a mean of 72. So remember, the 72 is going to be right in the center of our normal distribution, and we know that the when it is transformed, mu will have, of course, the value of 0. And we're going to have the standard deviation is going to equal 8. So we want to know what the probability is that a randomly selected manager will score above 60 on this test. So I'm going to do this two ways for you. The first way I'm going to do it is here as it is written, and then I'm going to draw it for you out on the normal distribution. So first thing we want to do is use our z formula that we were just talking about. We're going to plug in our values. So we've got 60 here. Oops. And we have the value that we're interested in determining is 60, right? We want to know the probability that someone would score a 60 or greater on the test. So we take 60, we subtract 72 from it, because that's the mean, and we're following our formula here, and we're going to divide by the standard deviation, which is 8. So we get negative 1.5, which means we're on the left side of our normal distribution, and we're about 1.5 standard deviations below the mean. So we're going to take our 1.5 and we're going to go look at our table there we can find in Appendix 1. We're going to look up negative 1.5, and we're going to find that the value is actually 0.066 when we look on our table, but because it's negative, we have to subtract 1 minus that, and so we have a 93% chance that a manager would score greater than a 60 on the test. Or it shouldn't be a percentage, actually. So greater than 93.32% chance that our manager would score a 60 or greater on the test. So now I'm going to show you the same exact problem, but we're going to do it drawing it out on the normal distribution. So what I've done off tape is draw out this beautiful drawing you see in front of you. I'm sorry, I'm not a better drawer. Now up here you see that I have written out the exact same formula that we had previously. Right here we've got 60 minus 72 over 8, and we see that that is going to equal a negative 1.5 right here. But I think it's a little easier to understand drawing it. So below here I have the normal distribution. We know that the mean for this sample is 72. So on average a person scores 72. And what we want to know is the chances that a person would score 60 or greater. So if we drop back one standard deviation here, we take 72 and we subtract 8 from it, we get 64. So right here, this -1 standard deviation has the numeric value of 64. And if we drop back one more standard deviation, we subtract 8 again, we're going to get 56. Because while each of these has the percentages represented here, 34%, So 34% of the population are going to score between a 64 and a 72. The value is 64 in this particular case and 56 here. So the question before us was, what's the chances somebody would score 60, which is right about here. I'm going to change my pin color. So what is the chances somebody would score right about here, this point here, this X, so this is about 60, we'll just say, roughly, or greater, so that's a 60 or all the way to the end of the distribution. So we know from the previous slides here that this part of the distribution is 50%. So we know it's greater than 50% that he's going to have scored 60 or higher. We know we have to add this 34% on here too because we're on the other side of that. So now we're at 84%. And then we have to also add this additional percentage right here, which is half of 13.5%. So it's all of this red. So I went back and did a little bit of calculating off the screen here, and you get pretty close doing it this way, which I honestly think is perfectly fine for anything you would ever do with this. And I know that you engineers out there, you hate it when it's not exactly precise, but because of rounding, because I'm using 34 instead of the exact amount, which is really 34.13, and I'm using 13.5 instead of 13.68, etc. You can get very close this way, so let's just go with that. So if you draw it out and you reason out the percentages, you can see that you've got this 50% plus this 34% plus about half of 13.5% is how I have it written. It actually should be 13.6%, I mean, which gets us a little closer. When we take half of that, we get 6.8, and that adds up to 90.8. So about 91% of the time, a person would score 60 or greater on this test. Now, if we take our 1.5 here and we go look this up on a chart, on a Z-chart, we're going to get this number 0.0668. And what this number tells us is that there's about a 6.6% or 6.7% chance that a person would score less than 60%. So that is this distance right here. There's a roughly 6.68% chance somebody would score less than 60. And then what is remaining on the normal distribution, 100 minus 6.68, so about a 93% chance that a person would score greater than 60. So the way we did it, we got about a 91% chance. There's always a little bit off when you get down here in the tails just because of the way the percentages work out and the rounding, but you get very close this way, and I think it's picture is worth 1,000 words when we talk about this sort of stuff. So now, what I want you to do is I would like you to try this next example of the empirical rule, and then I'm going to assign you a couple of homework problems that I really feel like it's important that you work through. So here's one more example, a little bit more straightforward. We don't have to interpret the decimals, and that is we have an investment strategy, expected return 4%, standard deviation of 6%. What's the probability of returning greater than 10%? So here we take 10, we subtract 4% from it, divide by 6, and we get 1. We look up our 1 on our Z-chart, and we get this 0.8413. So that is actually the percentage chance that we would earn 10% or less. But because of the way the question is worded, we are looking for the percentage chance that a person earns 10% or greater, which we know is probably going to be pretty low because, of course, the average is 4%. So we look this up, we get our 84%, but that doesn't seem right. So then we know, oh, well, wait a minute, we need to subtract this from 1. So actually, there's about a 16% chance that a person would get an investment return of 10% or greater. Now I'm going to show you this using a normal distribution as well, just so you can see it. So here I've annotated the numbers relevant to this problem. We've got the mean there at 4%. I've got +1 standard deviation here at 10%. And then I've drawn on here that the space here, represented by 34% of the normal distribution, is actually 0.06, because that's what the standard deviation is. So the question in this problem is the chances of somebody obtaining a return of 10% or greater. So what they're asking for us to tell us is the chances of getting here or greater. So all of this shaded area. So we know that it's certainly not going to be 84%, right? It's actually going to be this 13.5 plus 2.5, or roughly 16%. We say that this part of the normal distribution is about 16%. So hopefully that makes some sense to you as to why we look up the number and we get 84%, but yet the answer is actually 16%. So on the next slide, I'm going to talk to you a little bit about the importance of doing the homework problems to practice this. So one last thing I want to tell you about in this chapter is we can do some of this using Excel. We don't have to look up the numbers in the chart. We can actually get the Excel to perform the normal distribution function. So if you don't want to use the table, you can actually do this using Excel. You type in this normal.dist. You have to put in X, the mean, the standard deviation, and the cumulative of 1, which means that we're looking for a cumulative distribution as opposed to just pieces of it. You have to, the hard thing is remembering, which number goes where. So just remember that whatever number you're trying to solve for, that'll go in the first spot, and then you put the mean and the standard deviation and the cumulative of 1. Okay, so with that, let's talk just a little bit about the homework problems that might be relevant to this. So to practice this stuff that we've talked about, you should probably be able to do 18, 19, and 20 pretty easily. 34, 35, and 36, a little bit more challenging, and then 50 and 51 give you a nice overview of the concepts within this chapter. So I hope this is helpful, and see you soon. Bye.